G'day, I'm Dr. Kev, and this is Car Design Workshop. In this video, we're going to be looking at steering, how much we require, how fast the steering needs to be, and the amount of difference that we'd be looking for from the inside and the outside wheels, or as we'd call it, Ackermann steering. When considering how much steering we're going to need on a car, I want to consider three cases. One is going to be the minimum desired turning circle, and this will be where the car is doing a U-turn at a low speed, the minimum expected road radius, and lastly, the minimum radius that we would expect if we took this car onto a racetrack. This diagram shows the relationship between the turning radius of the car and the steering angle of the wheels. If we change the turning radius, we see that the required amount of steering also changes. As the turning radius decreases, we need more steering angle. As the turning radius increases, we need less steering angle. We see that this is not a linear relationship, and especially as we're going for very low turning radiuses, such as the minimum turning circle, we have to end up adding quite a lot of steering lock in order to see minor improvements to that turning circle. And the turning circle is the first of the three main cases that I want to consider. If we look at a minimum turning circle, that is going to be the diameter of the outside path of the outermost extremity of the vehicle. It is going to be a function of both the vehicle's size and the amount of steering lock that we can put on a vehicle. For Project 171, it's a vehicle that's not going to have very high overhangs. There won't be much of the bodywork in front of the front wheels, and there won't be much behind the rear wheels. So we can assume that the turning circle is really going to be a function of the track, the wheelbase, and the steering angle. Looking at the benchmarks we determined in an earlier video, we see that the turning circles are really around that 9 to 11 meters. The lowest of these is the Mazda MX-5, and the highest is the Jaguar XJ13. Well, it's worth noting that the Jaguar XJ13 was never intended to be a road car, more of a race car, in which we don't need to run as tight a turning circle. Now from this list, it does appear that the MX-5 is quite impressive, but we could probably live with a turning circle of around about 11 meters in diameter. If the vehicle is around 1.7 meters wide, then that's going to mean that we're going to need a minimum turning radius of slightly less than 5. So if we look at the chart again, we see that that's going to require steering angles at the steered wheels of around 25 degrees. The second case that I'd want to consider is the minimum turning radius that we would expect to encounter while driving along Australian roads. Now typically, while driving, this is going to be a 90-degree left-handed turn. Looking at some of the guidelines for road design in Australia, the recommended minimum inside radius for one of these turns is 6 meters, and the lane width is 3.5 meters. So if we take away the car widths, again assuming about 1.7 meters, we find that there's a path that the center of gravity of the car can travel on. And if we assume a constant turn radius, we can determine what the largest radius would be that we could pass through this road, going from outside of the lane to an apex to the outside of the lane. And that would be a radius of 13 meters. Now in practice, we're probably going to end up with a radius tighter than that because we're not going to be using the very outside and inside of that lane. We will leave some margin for error in driving. So we could imagine that we would expect a minimum turn radius here of around about anywhere between 10 and 13 meters. Now, if we look at the steering angle required for that, we see that it's quite a lot less than what we're going to need on the minimum turning circle. And to hold that radius, we'll only need about 10 to 15 degrees of turn at the steered wheels. Now, at this point, some of you might be watching and going, what about tire slip? And I'm going to assure you, I'm going to address that a little bit later, but we will need more steering than we imagine once we're actually starting to generate some grip from the car. Now, the last minimum corner radius that I want to consider is what we would expect to find if we took the car out onto the track. So if we have a look at this data, this is from a GT style car running around a typical Australian racetrack, and we're looking at the inverse corner radius. You can see that most of the time is spent at very low inverse corner radiuses, which means in the straights. But if we look to the edges here, we can get an idea for what the expected minimum radiuses would be. In this particular case, the minimum radius would be about 25 meters. This is expected. We would see higher minimum radiuses on a racetrack when we compare to a road, because we have got quite a wider track, and we are using all of the available road to really make that radius as large as possible throughout a corner. Now it's worth thinking about what defines the amount of steering that we're going to end up with on a car. And the two main parameters that we're looking at is the steering arm length at the upright and the amount of travel from the steering rack. An example I have here is a rack that I am considering for Project 171, which is a rack from a Mini. Now this Mini rack has 90 millimeters of travel lock to lock, which means 45 millimeters towards the right and 45 millimeters towards the left. And if you had an arm length or steering arm length of 100 millimeters, that's going to end up with about 27 degrees of angle at the wheels. One thing I should note is when I created the graph of steering angle required versus the radius, I was setting a wheelbase there. That wheelbase was set at 2.2 meters, the intended wheelbase of Project 171. But we can see that the turning circle diameter will be a function of wheelbase. If we increase the wheelbase, we're going to either decrease the turning circle diameter for a given steering lock, or we're going to need more steering for the same turning circle. In the example that I've given of the Mini rack with 90 millimeter travel from lock to lock and a 100 millimeter arm, that's only going to give just enough steering angle to reach the expected turning circle I'd want for the vehicle. So it's marginal. It could be made to work, but probably going to end up looking for a rack that's got slightly more travel than this. One option would be to reduce the steering arm length from 100 to a lower value, but in the end, I actually would like to increase that steering arm length, and that's going to be more apparent when we start to look in future videos around bump steer and some of the loading applied. The second issue around steering that I'd really like to consider in this video is the rate of steering. And this is going to be the ratio from the steering wheel to the steered wheels. A low steering ratio is going to be quite responsive. A high steering ratio is going to be a car that is less sensitive to movements. We also want to consider things like slop in the steering system. So if we have a really low ratio, any slop in that steering system is going to feel magnified. This is really noticeable if you drive a racing car with a really low steering ratio. You really need to make sure that all of the slop in that steering system is taken out. So a big question is, what would be an acceptable steering rate for a sports car? And here is where I would like to reference a paper written by one of the engineers working on the McLaren F1. In this paper, amongst many other things, they collect a few benchmark vehicles to consider the overall steering ratio. They gathered the Jaguar XJ6, the Lotus Elan, which is well known for being a very responsive car, a Ferrari F40, and a Porsche 928S. And if we have a look at the ratios there, the Jaguar was a 16:1, the Lotus Elan a very fast 14.5:1, and the Ferrari F40 a 17:1, and the Porsche 928 a 17.6:1. Now the author went on to talk about the McLaren F1 and what they decided to do, and the 17:1 felt quite quick in the car. They had changed it to a 19.6:1, and then changed it again to 18.5:1 when they had a change in the front tyre. Now it's worth noting here that the properties of the tyre are going to have an impact on how fast you want your steering rate. Now, I don't want to get too much into tires in this video, but it's somewhat unavoidable when we're talking about steering. Put simply, a tire generates its grip as a function of slip angle. Slip angle is the difference between the heading of the tire and the heading of the vehicle. If you have a tire where the peak force occurs at a really low slip angle, then that's going to be very sensitive when you're driving it, and you're going to need a higher steering ratio. Conversely, if you have a tire where the peak force is at a much higher slip angle, then you might want a lower ratio. And some of this might explain the differences between that Lotus Elan and some of the later vehicles. I would imagine that the Lotus Elan would have a tire with the peak slip angle occurring quite a bit later than the wider tire you would find on a Ferrari F40. So it is difficult to set these sorts of steering rates without knowing some of the data from your tires. However, one of the things that becomes clear from this paper from McLaren F1 and really from the different ratios that we see from the vehicles is that it would be very handy to make sure that we can adjust the steering rate. So that's probably working with an upright where we've got an adjustable steering arm, or the steering arm's able to be removed and replaced. And that's fully what I intend to do with this vehicle. Now, if I go back to the example that I've been using with the mini steering rack, with a 100mm steering arm and the full travel of the steering rack, we were seeing 27 degrees of wheel angle. This was occurring over 410 degrees of a steering wheel movement. This would give a ratio of 15.8 to 1. Looking at this compared to the benchmarks that were provided in that McLaren paper, that puts it a little bit slower than the Lotus Elan and a little bit quicker than the Ferrari and the McLaren. And I think that's probably not a bad place to be. When researching this, I did go and have a look at steering ratios of a number of different cars. I went online and found a number of different data points. And I thought that there might be some relationship between the steering ratio people were choosing and the wheelbase. And that didn't prove to be anything really noticeable. I did, however, see that there was a lot of these sports cars with a steering ratio of between 14 to 18. So that provides a boundary for the work that we'll be doing with Project 171. Now, the third and probably the longest point that I want to discuss in this video is Ackermann. Well, this is the difference between the inside wheel steering and the outside wheel steering. If we look at this diagram, we see that the concept of Ackermann steering is that for a given turning radius, the inside wheels are moving on a tighter circle than the outside wheels. So the inside wheels will need to turn more than the outside wheels. To achieve a difference of inside steering angle compared to outside steering angle, there's two main ways we can do it. The first is by angling the steering arms at the upright from a plan view, and the second is to be able to move the steering rack forwards and rearwards of being aligned with the steering arms. If we were to look at typical Ackermann steering, so what we would consider 100% Ackermann steering, then we would draw an intersection of those steering arms through to the center of the rear axle. If we were to design a car with 100% Ackermann, if we were driving along a gravel road, we really won't see any disturbance at low turning speeds. Or if we were in a concrete car park, we wouldn't really hear the tires squeal around those tight turns. Here's an example of the inside and outside wheel steer as a function of rack movement for the initial design of Project 171. We see that the inside wheel is turning more than the outside wheel. Now, one of the better ways, I guess, to look at this is to, instead of thinking about an inside wheel and an outside wheel separately, is to combine that and think of that as dynamic toe angle. Now, toe is just the difference between the two wheels. So if we take this graph that's got the outside and the inside wheels and instead plot the difference of that, we get this graph, the dynamic toe. And so this is the dynamic toe of that particular case with Project 171 versus the steering rack movement. Now I've set it so that the dynamic toe, when it's negative, indicates that it's toe out. And we would say that that is positive Ackermann. If I want to compare this to what we would consider 100% Ackermann, we would see that I've designed it with quite a bit less than 100% Ackermann to start with. A reasonable question to ask would be to ask how much is an appropriate amount of Ackermann to use, or what is the appropriate amount of dynamic toe to use. Referring back to that McLaren paper, they noticed that the Ferrari F40 had 40% Ackermann, and that's what they adopted with the McLaren F1. I'm not intending to build a car that's going to go as quick as a F40 or a McLaren F1, but it seems like a reasonable starting point. But let's investigate this a little bit further. First of all, I'd like to see how the dynamic toe as a function of steering travel changes as I move that intersection point forwards or backwards. So 100% Ackermann would be that intersection point of those steering arms being at the rear axle. If I have that intersection point rearwards of that front axle, I'm going to have Ackermann steering. As it gets closer to that front axle, we see more dynamic toe. As it moves further away, we see less dynamic toe. I can have anti-Ackermann as well. So if I move the intersection point of those arms forwards of the front axle, then the inside wheel is actually going to turn less than the outside wheel. And we would call that anti-Ackermann. And again, if that intersection point is closer to the front axle, we have more dynamic toe. And as it moves away, we have less. In the case where we have the arms parallel to each other, then we would have parallel steer and we would have no dynamic toe. And we can plot the dynamic toe versus that intersection point, and we see that it's a roughly hyperbolic function. As that intersection point gets closer, we get a lot more dynamic toe, either whether it's anti-Ackermann or positive Ackermann. And as that intersection moves away, it becomes much more parallel. You can see this in these lines of best fit. Now you will notice that when I've done this, the center point is not at 0. And that's because in the initial design, the rack is moved slightly forwards of that axis point. So the forward and aft motion or position of that rack has affected the amount of Ackermann. And we're going to look at that in a minute. But before we do, it's worth noting that the cornering condition proposed by Ackermann steering isn't really how a car corners. In order for a car to have some amount of grip, the tires must have some slip angle. Now, if we put a slip angle on the rear tires, we'll see that the center of turn of the car is not going to be aligned with the rear axle. It'll actually be forward of the rear axle. Now, if we were to capture what is the ideal dynamic toe for versus a steered angle when we include an ideal slip angle, we see that it is a function of both the ideal slip angle and that steered angle. And we see if the ideal slip angle for a tire is quite large, then we actually get an ideal dynamic toe that is anti-Ackermann rather than pro-Ackermann. So this is pointing towards the idea that we want to know for a given tire what is going to be the ideal slip angle for that tire. We can now plot this dynamic toe versus the corner radius with slip. And we can see that in those lower corner radiuses, we're going to want some Ackermann. But for the higher corner radiuses, once we bring in slip, we're probably going to want some anti-Ackermann. Converting this to a percent of Ackermann, so we're comparing the dynamic toe, the ideal dynamic toe for a steered angle with slip, as a ratio to 100% Ackermann, then we can get this graph where we can see how much Ackermann as a percentage we would want for different corner radiuses. Now, if we go back earlier, we see that there were 3 cases that we were concerned with. One that was the slow turning radius. Now, in that particular case, we are not going to want much slip on the car at all. We're not going to get slip. So in that particular case, we're likely to want 100% Ackermann. The next case that we'd look at would be the racing case, where we saw a minimum radius of about 25 meters. For that case, if we have a tire with a low ideal slip angle, we would probably want close to parallel steer. And that would be a tire, I would say about 5 degrees ideal slip. If we have a tire that requires more slip than that, then we're going to probably want anti-Ackermann. If we go to the case where we're on road again and we're looking at the tightest corner that we're going to see, that radius was going to be between about 8, 10, 13 meters. And we would see for really most of these tires, if we had a tire that was saying a peak of, say, 10 degrees slip, we would want a tire that has anywhere between parallel steer and 40% Ackermann. That's looking pretty good for the Ferrari F40. Now, I would say that given that this car is going to be designed predominantly for the road, and that's going to involve sometimes being in these really tight situations of minimum turning radius, we would want something in between a little bit of Ackermann and 100%. And so that 40 from the Ferrari F40 looks like not too bad an Ackermann percentage. Now, one other thing that would be worth noting here is that the ideal slip angle for a tire is usually a function of load as well. Now, I don't want to get too much into the tire here, but it is relevant. If we look at a case where a car has a tire where the ideal slip angle increases as a function of load, then we're going to see that the outside, more heavily loaded tire will need a little bit more steering angle on it compared to the inside. So the graph of the percent Ackermann versus cornering radius when we include this load transfer would indicate that we would need less Ackermann than if we didn't include the load transfer. Now, of course, this is very tire dependent. So I would think a reasonable amount of Ackermann to have would probably be between parallel steer and say 40–50%. And that's more because we are always going to have some of that low speed turning, and we don't want to have the car's front tires fighting themselves in those conditions. If we were to take this car out onto the track, however, that's where we would start to really want much closer to that parallel steer, or maybe even investigate a little bit of anti-Ackermann. Now, because we don't have this tire data and we're not likely to get a lot of this tire data, we can do some searching for data from similar tires, and I have done a little bit of that. And that does indicate that for a reasonable tire, we would expect that the ideal slip angle will increase as a function of load. But I think a good approach, as we did with the rate of the steering and the amount of steering, would be to make sure that the steering arm is something that can be altered as we go and develop the vehicle. That might be particularly important if we are looking to maybe make a racing version of this vehicle, or decide that we want to do a fair bit of competition with this vehicle. We would probably want different steering settings than we would want on the road. So the last thing I wanted to mention is there's one other way that we can at least get this Ackermann or anti-Ackermann in our vehicle, and that is moving the rack forwards and rearwards. Now, I've designed this rack so that it's going to sit forward of the axle line, and what that means that if I move the rack forwards, I'm going to see more anti-Ackermann. If I move the rack rearwards, I'm going to see more pro-Ackermann. So as the rack moves forwards, the outside tire is going to move more relative to the inside tire. And if I move the rack rearwards, the inside tire is going to move more compared to the outside. Now, in both the case of the rack either moving forwards or rearwards, or the angling of the steering arms on the upright, all it's really doing is changing the angle between the steering tie rod and the steering arm. If you have the steering tie rod at close to 90 degrees with the steering arm, then that's going to approximate parallel steer. If the angle between the steering arm and the steering tie rods is acute or less than 90 degrees, then we're going to have Ackermann steering, or we would see that as a dynamic toe out. If the angle between the steering arm and the steering tie rod was greater than 90 degrees, from a plan view, then we're going to see that that is going to be a dynamic toe in or anti-Ackermann. So if we plot that dynamic toe versus the fore-aft rack location, then you'll see that as the rack moves forward, we have less Ackermann, or we have a positive dynamic toe, or that's going to be toe in. As we move it rearwards, we're going to see more dynamic toe out. Now you'll notice that this doesn't intersect at 0 because the design does have some angle on the steering arms already. So note these graphs are really references to the initial design. Now there's a lot of discussion around the amount of steering that you would need, steering rates, and Ackermann, and I understand that you really can't be conclusive about this. Different cars have tried different things, and you can find cars that have varying different levels of Ackermann steering or dynamic toe that are really quite good. And that's because in the end, you do have to look at the tire performance. But I hope this video has given you an idea of some of the things that you need to consider when doing the steering design, and it certainly helped me start to clarify some of the design that I'm doing for Project 171. So please take some time to like this video and maybe make a comment. If you have any questions, I'm happy to try and get to those as I can. Thank you for your time.